everyone, and welcome to lesson 14 of atomic structure. As is always the case, I want to make sure that you're prepared for the lesson before we start. So put your phone away or put it on silent so you're not getting distracted. Make sure that you have the equipment you need, so your pen, your black or blue pen, your feedback color pen, a highlighter if you're using the booklet, as well as paper or your booklet to take your notes on. So with all that said, let's get started. As is always the case, I want you to go through this knowledge check and I want you to write down an answer for each one of the questions. Even if you're not sure, just give it a guess. I'll go over the answers in a minute. So hopefully now you've written down an answer for each of these questions and we'll go through the answers now. So the name for the electrons in the outer shell, we call them the valence electrons. The name of the domed shape caused by surface tension in water. So if you ever look at a measuring cylinder, for example, you'll notice that the water will always have a bit of a domed shape. That shape we call the meniscus. Why is water polar? Hopefully you remember from year 8 that water has this bent shape, meaning that on this side where the oxygen is slightly negative, and on this side is slightly positive because the electrons are here in the bond and so we're seeing the nucleuses of the hydrogen. So it's polar because of its bent shape. Means one side is positive and the other negative. Why are some substances insoluble? This goes back to the definition of what does insoluble means. It's because they cannot dissolve. The force between water molecules. So this is between two different water molecules. So if we have one and a second one, what force holds them together? And that is the intermolecular forces or intermolecular force. The bond between the hydrogen and the oxygen atoms, that is a covalent bond, because hydrogen and oxygen are both nonmetals. Give the name of the liquid that dissolves into a solid. Give the name of a solid that dissolves into a liquid. That is the solute. And the type of bonding found in salts is an ionic bond, because a salt is always a nonmetal and a metal together. So double check you have all the right answers. If you've missed one, that's fine. Write it in now. And then we'll move on in a moment. So today we're talking about mixtures. Now there's a lot of everyday mixtures that you are already aware of, that you think about on a regular basis, but we'll talk about the different types of mixtures today. So a mixture is made up of more than one type of substance in the same space, but not chemically bonded together. So to simplify that a little bit, a mixture is two or more atoms or molecules that are not, and that not is important, bonded together. This means that they are easier to separate. Because if they were bonded together, they'd be very hard to separate because we'd have to break those bonds between them. Now all we have to do is overcome the intermolecular forces. So mixtures can be made from elements, which hopefully you remember is one type of atom, only one type of atom. A compound, which is two or more atoms two or more types of atom. Bonded together. So we can have elements, compounds, or a mixture of both. However, in that mixture, the properties of each substance remain unchanged. So the properties stay the same. So for example, that we have here, we can have a mixture of iron. Now, hopefully you remember some of the properties of iron. You'll know it's a metal, which means it's solid at room temperature. It'll be shiny. You hopefully remember that iron is one of the magnetic metals, along with cobalt and nickel. So it's solid, it's shiny, it's magnetic, right? Whereas sulfur is a non-metal. So sulfur is a non-metal. So it is dull. In this case, sulfur is one that is a solid at room temperature still, but it's not shiny, it's not magnetic. And it's very brittle as opposed to iron, which can bend very easily. So when we mix iron and sulfur together in a test tube, for example, we get a mix of the two, but no chemical reaction takes place, so it does not make iron sulfide. So iron sulfide would be a compound, and it takes a chemical reaction to create it. But there would be no chemical reaction, so no electrons would be moving in any direction, so all we get is a mix of the two. So because the iron is magnetic, it retains its magnetic properties, so it stays magnetic. Whereas the sulfur isn't. So this means we can easily separate the iron from the sulfur using a magnet. So the magnet would attract the iron, it would come out of the sulfur, and they would be separated. Some mixtures may be very difficult to separate, but others are easier, but they are all possible to separate. It is always possible. Because they are not chemically bonded. So we just have to look at the difference in properties and find a property that's different between them and use that. So sometimes we can use something that we can dissolve it in water, or we can dissolve it in some other solvent, looking at the properties of what it is. So what I'd like you to do now is to go to this video. You can either click on the link in the booklet your teacher has sent to you, or you can just Google separating solutions, mixtures, and emulsions fuse school, and it will pop up on YouTube as well. So go through, watch that video, and we'll come back and we'll do some things that you've learned from there. That video talks you through some of the ways that you can separate different mixtures depending on the properties of these substances in the mixture. We'll be looking more in depth into all of those different ones later. First, we need to make sure that you understand the difference between a mixture and a compound and an element. So remember that a mixture is two or more things not chemically bonded. So a mixture is two or more not chemically bonded. That's a mixture. Make sure that you do have these definitions down because they will pop up again later. An element is only one type of atom. And a compound is two or more types of atoms bonded together or chemically bonded together. So looking at these 15 boxes here, some of them are mixtures, some of them are elements, and some of them are compounds. So I'd like you to go through and try to label the differences between them. So I'll give you an example of each. So this first one here, you'll see they're all one type of atom. The circles are all the same size and they're all the same color. So this one here is an element. If I go down, I can see that there are two types of atoms. So there's the gray one and the white one, so it can't be an element. But if I look and see, they're all bonded together in the same way. And so they are bonded together, but it's still only one type of molecule. So this one is a compound. And this third one here, I have some of the same atom, but a different type of atom as well. So it can't be an element. This is one type of molecule, and the atom here is on its own as well. So it's, again, not the same. So this must be a mixture. So now I would like you to pause the video, go through and find and label all the rest of these as well. We'll come back with the answers in a minute. Looking at here, you have all the answers to the substances. So you'll notice that some people would get confused on this one because they are chemically bonded together, but because there's still only one type of atom, it's still just an element. There's no second type of circle, so it is still just a single element. If any of the rest of these confuse you, make sure that you do email your teacher about it and they can help you with it. Now we'll have a look at some different examples of some mixtures, some of which you might be using right now. So the first example we're going to look at is pen ink. You might have your favorite blue pen, and then when you pick one up of a different brand and go to write with it, you'll notice that the color of blue is a little bit different. That's because each company will blend different mixtures of the different colors together. So it will never be the exact same if it's a different company. Scientists or anyone who wants to see how the different colors in that particular ink can separate their colors. We can have their colors separated by a process called chromatography. So chromatography separates colors or any mixture based on the solubility of the components of that mixture. So for example, if one thing is a lot more soluble in a liquid than the other, it will move faster, and we'll look more at that in a little bit. Another mixture that you deal with every day is your blood. It might look like a completely clear liquid coming out, which would mean it is a homogeneous mixture, but it is a mixture of water, cells, and other molecules within that. So for example, if you have a blood sample drawn at the hospital or at the doctor's, they might need to try to separate out that blood. When they do that, they separate it based on their mass or how much of the cell there is. So for example, a red blood cell has less mass than a white blood cell. So knowing that, they'll be in different layers once it's separated out by a process called centrifugation, which essentially means that it spins really, really fast. The same way that heavier people tend to fly more to the outside on a merry-go-round than others. And one last example that we're going to look at right now is rock salt, which is what they use on the roads in the wintertime to keep it from getting too slippery. So it's a combination of salt and small rocks or sand, which is why it's called rock salt. It has the rocks or the sand and the salt. So both of those parts are a very useful part in that. So the salt lowers the melting point so that the ice is less likely to be ice and more likely to be just water, which is less slippery. And the sand or the rocks is used for grip so that the tires on the road or of your bicycle or your feet have more traction on the ground. So we can separate it by process of dissolving because one is soluble in water. The salt is soluble in water and the sand isn't, and then filtering. This was an example they showed in the last video you watched from Fuse School. So as I said, we'll look more now into chromatography, which is the process of separating based on solubility. So chromatography is a process used to separate different colors in some inks, dyes, and paints. So that is the most common use, is to figure out what's in that mixture of inks or in that mixture of different pigments and things like that. So each ink in the mixture will dissolve in water, or it could also be any other solvent. Remember, a solvent is a liquid that dissolves another one. So it will dissolve in water in a different way. Some are more soluble than others. So in chromatography, the more soluble ones will move farther, and the less soluble will stick to the paper. So it depends on how attracted they are to the water. So if we look at the picture here, what happens is you start with your samples on the start line. We use a pencil to draw this start line because hopefully you'll have realized that pencil won't dissolve in water. So that pencil line won't move. But the ink will smear with the water when the water moves. So as it goes on, the water, the solvent here, which we mostly use water, but we can use other ones, will move up the chromatography paper, or filter paper is sometimes also used, and it'll take that ink with it. So you'll notice B here makes only one spot, so it doesn't get separated. So B is a pure substance because it has only one spot. Whereas A is a mixture because it has formed two spots. The first spot, the one that's lower, is an ink that is less soluble than the one that's higher up because it's traveled less far. So it's less sticky to the water and will stick more to the paper. C, you can see, is also two spots. We see that these two spots here are the same height, so they've traveled the same distance, so they will be the same compound or the same element because they've traveled the same distance. So each compound will travel the same distance within the paper, starting with the same point. So to learn a little bit more about it, there's a video here I'd like you to watch. So again, there'll be a link in your booklet or under this video, or you can just Google the name of it and it'll show you how to do chromatography. Some of you might have a coffee filter and some pens lying around at home, so you could give this a try at home if you would like. Otherwise, you will get a chance to do it at some point at school. So as you saw in that video, the RF values are something we use to measure how soluble something is. So if we look at our diagram here, the same as was on the last page, we'll be able to calculate the RF values from this chromatogram. So our RF value, the formula for that is the distance traveled by the ink divided by the distance traveled by the solvent. Something to keep in mind is they need to be measured from the same point. So in this example, it will be from the pencil line in the diagram. So we would measure it from the pencil line. So we need to be able to calculate this. So the first thing we need to look at is the distance the solvent traveled. So that 80 millimeters. That is from this line here all the way up to this line here. That will be the 80 millimeters. So the solvent, in our case the water, has traveled 80 millimeters, so that's the value that goes on the bottom. So each of these will be, so our RF is equal to a number over 80. Remember, if it's over, that's the same as saying divided by 80. So for this first one, sample A, so that was our first ink, it's moved, we're talking about the spot that's moved 12 millimeters, so that's this one here. So that would be 12, would be that value there. So our ink has traveled 12 millimeters. You'll notice for the ink sample, there are actually 2 spots. So there's actually 2 RF values for sample A because there's 2 compounds within it. So if you plug that into your calculator, 12 divided by 80 gives you 0.15. This is the one case in science where you don't need a value to that. The RF is just a number. So we go on to our next one, our 46. So that would be this spot here. So our RF is equal to 46 divided by 80, which again, you plug into your calculator. And end up with 0.57. Which you can round up to 0.58. Again, there's no unit for that. You should now be able to calculate the RF value for these last 3 spots. Pause the video, give it a go, and I'll be back with the answers in a moment. Hopefully you have these same answers here as I do. If not, have a look to see where you might have made that mistake and make your corrections. Hopefully you can see that there is no value larger than 1. You will never have an RF value larger than 1 because the spot is being carried by the solvent. You're never going to have a spot that goes further than the solvent. So it's always going to be a smaller number divided by a bigger one, which will always be between 0 and 1. So now that you've had a chance to make sure that you understand, especially this particular chromatograph, as well as how chromatography works, there are 7 questions here that I need you to answer. So you'll notice some of them are justify your answer. So you need to explain why that is. A lot of them we have talked about this, so give it a go. We'll go over the answers in a minute. So looking back at the chromatograph, which sample is a pure substance? As I said on the last page, a pure substance is if there's only 1 spot, so that would be B. So the answer here is B, and justify your answer. There is only 1 spot for B. 2 samples contain an identical ink, that would be A and C. Again, because we know this because there are spots at the same height for A and C. Which sample has the most soluble ink? That would be, again, C, because it has the ink that moved the most far. So for 4, most soluble ink, C. And we know that it has a spot that has traveled the farthest. You could also say it has the highest RF value, because it had that 8.5 where the rest of them were smaller. The sample with the least soluble ink, you look, and that would be A, would be this spot here. So that would be A. And again, because it's the opposite of 4, so it has a spot that has traveled the least far, or it has the smallest, RF value. So adding any corrections that you need to the answers you have. And then there's some more questions on the next page, just to sum up this whole lesson and about all of the bits of this lesson. So go ahead, give those a go, and we'll go over the answers in a moment. So mixtures are made up of more than one type of substance. Elements are made up of all of the same type of atom. The two phases, we have the mobile phase and the stationary phase. Three examples of everyday mixtures. There's all kinds of different things you could do there. The three that we talked about in the booklet were pen ink, blood, and rock salt. A substance that is dissolved in a solvent is called the solute. What a small RF value means about the solubility of the ink, it is not very soluble. Remember, the larger the RF, the more soluble it is. How many spots a pure substance would make would be 1. Why we use a pencil to draw the baseline, because it is insoluble, or it means it will not dissolve in water, which is the solvent we were using. And then these further questions take a little bit more thinking about it and a little bit more writing. So explain how you'd use chromatography in forensics to match ink found at a crime scene to that found on a subject. So you would compare the RF values of both inks to see if they were the same. So you could either compare the RF or you could compare the actual chromatographs, which is the paper you're left with after you've run the chromatography, to see if they were the same. A sample of sugar coating on some sweets is sent to the laboratory to investigate how many different dyes were used to make the coating. A sample produced 3 spots. So it gives you the distance they traveled and the distance traveled by the solvent. So calculate the RF value. So RF, remember, is the distance by the solute, or the ink, divided by the solvent, distance traveled by the solvent. So for our first one, so we have 3.5 centimeters divided by 15.7 centimeters. Notice that they are both in centimeters, so that's all right. If one was at a different value, we'd need to change the numbers. We'd need to convert it. So plug that into your calculator. 3.5 divided by 15.7, and we end up with 0.22. Again, that doesn't need any units because an RF value doesn't have units. And then we go 8 divided by 15.7 gives us 0.51. And last but not least, 13.2 divided by 15.7. 0.97. So from these, which one would be the most soluble? That would be the one that's moved the farthest, and the least soluble would be the one that's moved the least far. From question 2, explain how the company could check to see if one of the dyes belonged to a banned group of food pigments. You would simply compare the RF values. Because remember, the RF value shouldn't change depending on what it is, because it's that comparison. So if you use the same solvent and the same ink, it will always be the same RF value. So that's the lesson on chromatography and beginning of mixtures. We'll talk a little bit more about mixtures in the next lesson. If you have any questions, make sure that you do email your teacher and give your Educate quiz a try if your teacher has assigned one.